Hello again. What we learned in our previous videos is the spring elements that goes along the x-axis only, which is too simple. Okay, so we need in this chapter we're gonna learn something new, which is an element that will goes along the y-axis as well. Please take a look at the figure here. Okay, we have a spring element. Okay, but it's tilted by an angle theta. Okay, and again, it has the two nodes, node I and node J. Anything that moves along the I is called U. Anything force acting on I is a Fi. However, all the name has a hat on it. Okay, so we put everything in the matrix form. F hat vector equal to stiffness matrix times U hat vector. Okay, we expand that terms. Okay, it becomes a force vector ij equal to k stiffness matrix 1 1 negative 1 negative 1. By the way, this is the stiffness matrix for all spring elements now, and this is standard formation of the spring element stiffness matrix. And then we have times it by a displacement factor ui uj hat. Okay. By the way, so far what we learned here, nothing fancy. It's just a review of the spring elements. Nothing changed. Only difference is we have a hat on the force and a displacement vector. Okay, we want to have the y terms, okay, involved. So we add the ix, iy terms in it. Okay, and then we expand the stiffness matrix. We all know in this case, you all the movement along the y hat. Oh, by the way, I missed that. Okay, all the movement along the y hat is 0, so we just put 0 on the terms. Okay, this step to this step is totally the same. Okay, we just add the y terms in it. Now we want to know all the movement along the head reference frame. How does it affect what we what we see in the regular reference frame? Okay, now let's take a look at the first term here. Uix without a hat is equal to Uix cos theta, which is right here. This portion is a Uix cos theta. Okay, and then at the same time, the movement along the IY head will contribute a little movement on the regular reference frame. So this term, this portion right here, is UIY sine theta. Okay, similarly, for the if I want to find out UIY without a head, which is a UIX sine theta head, this portion is this one. And UIY cos theta is right. Yep, that's right here. So similarly, we do the same thing for UJX and UJY, and we express everything in a matrix form. Just put 4 equations into matrix form, and we get this. Okay, so this is your transformation matrix. What it does, if you times the force vector with the hat with this transformation matrix, you get all the force along the regular reference frame. Same here for all the displacement vector along the head reference frame. It also called local. You can do that, and then you can transform into the regular reference frame, and also we call it global reference frame. Okay. you can change the global reference frame to the local as well by having the transfer matrix inverse. Okay, we put this term into the first equation here. So we get this, and we manipulate the transfer matrix to the right. We get F in the regular reference frame equal to these terms here times the U in the regular reference frame. Okay, and we multiply the three matrices together. We have the stiffness matrix for the trussed element, which is the spring element at an angle. Okay, and in the next video, we will go through one example and show you how to use that stiffness matrix. Thank you.